Okay, so beginning chapter 12, the second chapter that covers the Jovian planets, and it's going to focus on their moons and rings. Um, Also, kind of squeezed into this chapter is going to be a bit of a quick discussion about dwarf planets. So we'll return to talking about Pluto. Luckily, we talked about Pluto quite a bit in the introductory chapter to the solar system. Okay, so we definitely already know what a definition of a dwarf planet is. And so I will only be briefly touching on that material. So consider the main focus of this lecture the moons of the Jovian planets, going one Jovian planet at a time. So covering the moons of Uranus, then Jupiter, then Neptune, and then Saturn. Kind of a unusual order, but mostly just kind of perhaps going in interesting order, saving some neat moons for last. And then a summary about rings around the Jovian planets. So the Jovian moon count is as follows. Here are our four Jovian planets that we covered last time. Jupiter's got 79 of them, Saturn a bit more with 82, and despite not being as large or massive, and not exactly sure why it has more, but it does. And then kind of similar numbers, but going down as we go out to the edge of the solar system, 27 for Uranus and 14 for Neptune. It certainly seems natural that these much smaller Jovian planets would have fewer moons, less gravitational strength after all, and that the numbers reflect that. But we're not going to talk about all, you know, almost 200 of them, of course. And there's many that I don't know anything about. And honestly, many of them are just small asteroids, essentially. They're not asteroids anymore, they are moons, but they're captured asteroids, and there's not much to say. They have a potato shape, no differentiation, um, and from there you could talk about kind of the general composition, but that's about all. So shown here is a kind of selection of the moons we are going to talk about. So the ones that are filled in are going to be the discussed moons. There's little images for each of them, not that you're expected to recognize them. And the reason that they're ordered in the way they are is they represent the not sure because it's not going to be no, no, it is distance. It is distance. Yep, it's distance from the planet. Because I was thinking that one of these is closer, is the closest, but there are actually smaller moons that are closer. Yeah. So these are just the dots that are empty are, well, I just said we're not talking about them, but they're in the first empty dot in each case would be the closest moon to that world. And in each case, we're not talking about that closest moon because every one of those closest moons is just a small rock and isn't of particular interest. Okay, so I did want to point out that there's four moons we're going to talk about for Jupiter, just two for Saturn, just two for Uranus, and just one for Neptune. So there are nine interesting moons. So quick rundown about moon sizes. How big are they? Well, some are quite big. Ganymede, the biggest moon in the solar system, is very, very significantly big, and you'll be able to kind of have a comparison in a second. Next up, the second biggest moon in the solar system is Titan, and both of them are bigger than Mercury. So these are two moons that are actually bigger than a planet, albeit a very small planet. But Mercury is quite a bit bigger than our moon, which we'll see as we continue down in scale. Obviously, all of these images are scaled, which is pretty neat. So next up in size is Callisto, then Io, then our moon, which I made a big deal about, is a big moon, and it truly is. By any standard in the solar system, and in particular for our planet. But compared to the really big ones, Callisto, Titan, and Ganymede, it is has a radius that isn't quite half the size, but is significantly smaller. Europa, Triton, and then all in comparison to Pluto. So that means that we have and this actually is a number that we saw way back when we did our introduction to the solar system. But we have one, two, three, four, five, six moons that are bigger than the biggest dwarf planet. But again, Pluto is the kind of arguably tied for the biggest, but not the most massive. And here are um, Tatiana and Oberon, which we included because they are of the nine that we're going to talk about. There are plenty of other ones in between that, for size references, but these are the next two we're going to talk about. So certainly our focus of quote unquote interesting moons is the big ones. Is that just a bias? I mean, like, hey, just look at the biggest moons. Yes and no. It's also that these are the moons that tend to have the most interesting features and the interesting features that set them apart. Well, once they become smaller, there's a certain uniformity to them. And Enceladus is a kind of an exception to that rule, and maybe is a indicator that there's a lot of moons that we discount that have, fascinating phenomenon that we're missing. Quite possibly the case, right? There's not been that many observational missions to carefully look at every moon. Often we just know a bit about their orbit and have never done a close flyby. Because look at Enceladus. This is one of the nine moons we're going to talk about. And it's absolutely in a category of tons of other small moons that we're skipping over. But there's some special features about Enceladus that make it worthwhile to cover. So as promised, starting with Uranus as our first Jovian world to discuss its moons. Well, the six largest of them, not that we're going to talk about all six, we're just talking about two of these six, but the six largest are Puck, Miranda, Ariel, Umbriel, Oberon, and Tatiana. Do these names sound familiar? Well, maybe they do if you're into classical literature or Shakespearean plays. Or maybe you're not, but you just, saw some adaptation of the Shakespearean play that all these names come from. And I'll mention that again in just a moment if you're, half remembering or interested. So here is our first moon of interest, Uranus's moon, Tatiana. It's a rock and ice moon. So as opposed to being like all rock, that's mostly what we're going to see, rock and ice moons. It has a density that's pretty similar to the density of Pluto or other Kuiper belt objects. The reason that this is a fairly low density is because of the large amount of ice. Okay, so it doesn't have as much rock as, say, our moon. It is the largest moon around Uranus. Has no atmosphere at all, so you could say it shares that in common with Earth's moon. So Tatiana has scarps like Mercury, and do you remember those? If so, where did they come from? Where did Mercury's scarps come from? Let's see who remembers this. I think it was on the test. Right? Maxwell says three. Maria says five. So it turns out I got one more. One from Isabel. Well, variety of answers. Oh, I guess sorry, one more came in. I can't have to look. I guess it was that same one. All right. So the answer is the shrinking of the planet. So Maria had it. And it's interesting that one of you, I think it was Maxwell, said it was the number three, because those are the Riles on the moon. And it's really easy to mix the two up. Um, well, the Riles do look more like ditches or canals than cliffs, where the scarps do look like cliffs. But it's that the idea that there's these specific features, and keeping the name straight isn't always easy. And that's why it's kind of a good thing to review. And then in terms of water, what looks like dried up watersheds, and almost certainly our dried up watersheds are on Mars exclusively. There's no other world, so planet or moon, that has the evidence of liquid water on the surface, but now completely gone, except for Mars. Okay, Mars is the only one. All right. So in the case of Mercury, the scarps came from shrinking, and the follow-up to this, so great review question, but now don't confuse things because it turns out that Tatiana's scarps were actually caused by the planet expanding. All right. So this expansion also formed long valleys too, similar to the Valles Marineris on Mars, and that one did come from a not a planet-wide expansion of Mars, but from an upwelling of magma. If you remember our discussion. So, why did Tatiana expand? Probably because of tidal heating. So that's a idea that we're going to see a lot. So hold that thought. We're going to talk a lot about tidal heating. These planets can get easily warmed up, and at some point, it seems like Tatiana got particularly warmed up and actually expanded as a result. The second of the two moons of interest of Uranus, and the second of two that we will talk about, is Oberon. It's also all rock and ice, a little bit less dense than Tatiana. It's just the second biggest, and likewise has no atmosphere. And almost I laugh because almost for lack of a better thing to talk about, because there's just not too many features to talk about with these moons. You know, the scarps were about all for Tatiana. So instead, let's talk about their names, and they are the characters from both mythology, but probably better known from the play *Midsummer's Night Dream* or any of its adaptations written by William Shakespeare, where Oberon was the king of the fairies and Tatiana was the queen of the fairies. And as far as moon nomenclature, while we're on the topic, well, Uranus's moons are all named for characters by William Shakespeare or Alexander Pope. So they all come from these literary names. The names of Mars's moons, those two small rocks, are the sons of the Greek god Ares. And so that's the Romans version of Mars. So since we got Mars, Ares, it makes sense to link the two between the two, basically mythologies. With Jupiter's moons, they're mostly children or lovers of Jupiter or Zeus. And there you're seeing that there's going to be a mix of Greek mythological names or the Roman equivalents, because not that it's important to know your Roman history in this class. That's kind of there's a feature that happened where the Roman polytheism just took all the Greek gods but renamed them, and we see that with a lot of the names that have been chosen for these moons. And Saturn's moons are named for the Titans, which are the predecessors to Greek or Roman gods. So the powerful beings that came before the quote unquote gods like Zeus. And lastly, Neptune, its moons are named for the Greek ocean gods. So you see that there always is an intention to sort of like have the names all fit a theme, so that maybe it's just fun, but really it's so that you can easily kind of recognize what planet they come from in certain cases. There are also exceptions for the really small moons that are far out, and they sort of almost represent separate orbital bands. There have been separate nomenclatures that have been chosen. So if you go to Wikipedia and look up Jupiter's moons, right, you'll find that there's these two groupings of really small, essentially asteroid captured moons that are very distant from the planet, and they fall into either being named all after Norse gods, or I don't remember the other grouping. So, they're much more modern, right? Whereas all of these names are made, at least a couple hundred years ago, or 100, 150. So now let's move on to, check the time, the moons. We're doing good. The moons of Jupiter. So we're done with Uranus, moving right on to Jupiter. We have a bit more to say about these moons. You notice right away that they have a special name given to them, the four moons of interest that we're talking about. They are called the Galilean moons. So remember that they are all moons of Jupiter, but more often you might hear them referred to as the Galilean moons. And that's because they were all discovered by Galileo, and they're a famous part of his supporting evidence of the heliocentric model of the solar system. Because although they didn't directly support it, they implied that if it's possible for other objects to have things orbiting them, in this case, Jupiter having moons, well, then perhaps Earth is not as special as we thought it was, and everything doesn't have to revolve around us. So, therefore, we could orbit the sun. So, what are these four moons? They're Io, Europa, Ganymede, and Callisto. And this ordering is in order of distance from the planet, distance from Jupiter. In each case, we're shown a image that shows the whole planet and then some zoomed in images in color and then in black and white, where they kind of serve different purposes because the black and white can be good for showing contrast to show elevation, or of course, color can let you know about, actual like phenomenon going on, like why is there a big red spot on Io, for example? And the evidence that Jupiter's large moons likely formed by accretion in a disk of material surrounding Jupiter is, or are, and if there's more than one point of evidence, more than one of the above. So it is actually all of these, no, just two of them, that apply to, let me see if this is show which one's got. And then this, I'm not sure why it's asked again, because there's no extra information. And let's see. So we have, yeah, I think this second slide is just a typo. So we'll just stick or put there by mistake or unfinished or something. Um, However, this one we'll briefly talk about. And I know I jumped to the answer, but hopefully you had a chance to think about it yourself. So we want evidence that these large moons were likely formed by accretion. All right. And that means that they came together with matter sticking together, essentially, right? It's that space version of the snowball effect. And accretion is the same process that made each of the planets, right? The accretion of planetismals into planets. In this case, you could say it's the accretion of rocks into moons, or, you know, moonlets or something, you know? But what actually supports accretion? Well, orbiting in the equatorial plane does, because that's all the matter that accreted or coalesced, to use a synonym, into Jupiter would have been in a disk, because it would have been part of the disk of the solar system itself. So if you have accreted moons, they are going to be in that same plane. So being equatorial is evidence of accretion. Revolving in the same direction that Jupiter rotates is also evidence of accretion, because all that matter that made the moons would have had to originally be revolving in that same direction. It could not have just naturally, by chance, be spinning the other way. That the whole system had rotation in one direction, and all exceptions had to happen because of gravitational interactions between larger objects, either from collisions or slingshot effects, and only later in the solar system's history. Okay, so there would have been no opportunity for anything during the accretion phase of the solar system to be spinning the wrong way. Because when there's lots of little pieces to bump into, that very process necessitated that everything spun in the same way, both around the sun and then around each individual body as well. Having densities which decrease with distance is not support, and it is not even true. It is a common misconception. I'm not sure if it's one that has ever confronted any of you, but it really does seem tempting to think that denser planets are are by their very nature going to orbit closer to the body that they orbit. Because isn't it true that denser material sinks to the center of planets? Isn't that what we talk about when we talk about differentiation? Yes, that's gravity acting in a system where there's things are not orbiting, right? The matter inside of a planet is not orbiting that planet. It's at rest relative to the center of mass of that planet. And it's then just able to get pulled directly down under the influence of gravity. When we talk about orbits, density has nothing to do with it because orbits are not just driven by a downward gravity that lets denser material move inwards. Instead, every body that's in orbit has a gravitational force that is being completely allocated to the centripetal force, thus allowing for a stable orbit. That's all that matters for orbits. And the mass and the density of the body that's orbiting has nothing to do with it. Orbits do not depend on the mass of the moon, let alone on the density of the moon. Same thing goes for orbits of planets around the sun. They do not depend on the mass of the planet nor on the density of the planet. They only depend, the Kepler's third law, they only depend on the period and the semi-major axis. Okay, the mass does not matter. So, last thing I'll say is the reason that this pops up as a misconception, um, more than it might just because of the assumption that denser things are going to move towards the center, since it, after all, does apply to systems that are at rest. Okay, again, orbit is not at rest. It's a key difference. But the other reason is because of patterns that, if misunderstood, seem to support the misconception. What are they? Well, look at the terrestrial planets. The terrestrial planets are all much denser than the Jovian planets. It might be easy to say that the terrestrial planets are denser because they sunk into the inner solar system. Now, that's how they got there, right? Absolutely not. They're just denser because all the low density material got blasted away from, solar radiation and the solar wind. So we've talked about atmospheric retention quite a bit. So their formation there, the fact that they're there, is the reason they're dense because they happen to form there, not that they were dense and therefore formed there. So it's the different order of cause and effect. So, keep that in mind. I've certainly seen it pop up in my classes. So, and this one here, although, having circular orbits is, um, totally believable. Plenty of moons do have, circular orbits. The Galilean moons don't. They actually have fairly elliptical orbits, at least in, the sense that we talk about elliptical orbits being, significantly elliptical. When you look at it, you're like, that looks a lot like a circle, because even a little bit of elliptical orbit matters when we talk about orbits. And so they don't, it's not true. They don't have circular orbits. So I guess we can cross it out. And if they did, it wouldn't be direct support of accretion. It is no way directly correlated. They could, there's no reason, there's nothing to say they can't, but it also doesn't support accretion. And furthermore, one of the moons that we'll talk about that has an almost perfectly circular orbit isn't an accreted moon. So that's at least one point where you can see that you can have captured moons that have circular orbits. So this is certainly not a criteria. And that idea, captured moons, I've been wanting to mention that. So I want to point out that, well, a lot of related ideas here, but the accretion process to make a moon, what is it? What's the opposite, so to speak? Like, because, the questions asking about them being made by accretion, that's all fine, But then how else do you get a moon? Sure, some of you know because I mentioned it in passing a few times, but really there's going to be two ways that a Jovian planet or any planet for that matter has a moon. Either accretion, okay, and that accretion can get complicated by cases, special cases like our moon, but still that generally you could say that it was made by accretion, but just with special extenuating circumstances. But still matter accreted. Um, and it definitely meets our moon definitely meets the supporting evidence criteria of being in the equatorial plane, pretty close to it, and revolving in the same direction, which we'll always see. But the type of moon that isn't is the captured type. So that's really what you always got to ask yourself. Is the moon a accreted moon or is it captured? Because it will always be one of the two. And captured means that it formed somewhere else. The accretion happened somewhere else, probably as a body orbiting the sun. So it accreted directly from the solar disk, also called the protoplanetary disk, and then through gravitational interactions got pulled into an orbit around the planet that we see it orbiting today. All right. So just a couple more minutes and we'll take our break. I'll say we'll take a break at 9:10. So expect 5 more minutes. So these four large moons, they're like a little mini solar system. There's they're all like nearly planet size after all, with Ganymede being bigger than Mercury, and Callisto being not much smaller, and sure, Io and Europa being smaller, but still pretty big bodies. And there is a lot to talk about with them, quite a few interesting features. Okay, so we have their interiors generalized right here for Io, Europa, Ganymede, and Callisto. Io and Europa have rocky mantles and metal cores. This is quite unusual of moons in the solar system. The vast majority of moons do not have rocky mantles and metal cores. They're going to instead be more like Callisto with a mixture of ice and rock, and then or like Ganymede with a icy upper mantle and a rocky lower mantle. So to have much more of the mantle be predominantly ice with suspensions of rock. And when we talk about undifferentiation here, um, it's sort of I've actually seen that in reference to Callisto before. It always kind of takes me aback because it seems like a contradiction. How can Callisto be round if it's undifferentiated? And the best explanation is that it went through differentiation, but there just wasn't anything to differentiate significantly, at least. So I I don't think it would hurt to point out that there is almost certainly some amount of core, some denser material at the very center, but it would be an insignificantly sized core overall. And in general, the material was so uniform that it's just the same all throughout. There wasn't any denser material, at least not a significant amount of it, to sink. So gravity still made the planet round, but since all the building blocks of the moon were more or less uniformly dense, they stayed that way. And so just to reiterate that this type of rocky mantle and metal core, which is like a planet sort of cross section, especially for Io, is not the norm with moons. They're going to be more like, these are going to be the moons of certainly Saturn, with one exception. Absolutely, if we saw a cross section of the two moons that we just talked about for Uranus, they would look like this undifferentiated ice and rock. All right, with maybe some expectation of a small core, as I mentioned. Same for the moons of Neptune. They're going to be, and also the same for Pluto. We talk about, yeah, Pluto has some layers, but predominantly this ice and rock mixture, not a mostly rock mantle. Okay, so this is really the only time you're going to see it. Think about Io as being a standout. Here are their distances from Jupiter. They're measured in radii of Jupiter. Io at 5.9, Europa at 9.38, Ganymede at 15, and Callisto at 26.3. So you can see that the spacing is such that Io, Europa, and Ganymede all orbit close to each other and, generally speaking, close to Jupiter. And then Callisto is much further out, right? Almost being twice as far as Ganymede. It doesn't interact in the same way that the three other moons do. And by interact, I mean interact with each other. More on that in just a moment. Their orbital periods are given here. All these orbital periods are listed, although the units are left off. They're listed in Earth days. Yeah, Earth days. So they're all pretty fast. That's normal of these types of moons because of the large amount of gravity coming from the planet. When you have a big planet, you can have stable orbits with with much shorter periods because of that much stronger gravitational pull, right? And of course, the contrast I'm referring to is our moon, which is nearly 30 days for its orbital period. Their densities are given here. The densities being in actual kilograms per cubic meter. I say that because we've mostly seen the units in grams per cubic centimeter, where it's always just a single number and then point. So if I was to convert this to the unit that we have been seeing for density, it would be 3.5, 3.0, 1.9, and 1.9. And so notice, right, 3.5, that's like, terrestrial planet density or, density of our moon, lower density terrestrial planet. So not like the 5.5 of Earth, but certainly comparable to our own moon. That is unusual. In fact, it's basically only these and maybe Titan. So one reason to call attention to these different values is because of this fascinating idea of resonance. What does it mean that there's orbital resonance with these worlds? And, like, why do we care about that? Well, we actually won't cover all the kind of future ideas, but it's an important idea for orbits, and this is kind of the most clean demonstration of it. But we will talk about it after the break. So I'm going to pause everything for now.
All right, so continuing with chapter 12 on the Galilean moons and all moons actually of the Jovian worlds, but talking now at the moment about the Galilean moons and specifically Ganymede, Europa, and Io. We mentioned that they are in resonance, and one consequence of this orbital resonance, and more on what that means, is that the occasional tugs pull the moons into slightly elliptical orbits. This happens at conjunctions marked by the flashes of green or gray or magenta in the animation. So let's take a look at that. All right, you're seeing it right now. You can zoom in a bit. So taking a look at this animation, just to point out those flashes. So whenever Europa and Io are in conjunction, that's when they flash green. And you can see that that happens every 2 orbits of Io. That's why the Europa period is listed as 2 to 1. Okay, Io shows a ratio of 1 to 1 because it's just showing that it's proportional to itself, or just related to itself. It's the comparison. Ganymede has a proportion or a ratio of 4 to 1, which means that for every 1 Ganymede orbit, Io orbits 4 times. Okay, so now you see what we're talking about, but what's special? Why is this called resonance and not just orbits? It's because of those exact ratios. It's because of this regularity of having the moons meet up at the same point in their orbits after a certain number of orbits for each of them. And that's not the way the planets work. None of the planets are in resonance with each other. We don't have conjunction with Jupiter a even number of Earth orbits relative to Jupiter's orbits. And the reason is because we're just too far apart to have had a significant gravitational force cause resonance to happen. But when gravitational bodies are close enough to each other, they'll naturally reach a form of resonance. In the same way that we so often see tidal locking as a natural consequence of orbit. Same thing when there are multiple moons that have significant gravitational interactions with each other. We end up with resonance. It's interesting because there's not really another good example in the solar system of resonance. I think there are a few that are, kind of showing that there's a trend. If you want to look at other good gravitational resonance examples, you have to look outside the solar system because it does occur with exoplanets around stars when they orbit very close to the much smaller stars than our own sun. So there are some really good examples out there around in other solar systems. So regardless, the physics is familiar. And that's why astronomers like to talk about it, since this is such a physical science. It's this natural process that we see, in man-made machines and so on, that there's always this trend towards resonance when there's significant force interactions. Okay, so I'm going to go back to the slides now. Okay. Go. Maxwell says there's 282 moons right there. Yeah, it's true, right? Yeah. Think about all the exoplanets out there and all their moons. Or just think about all the Kuiper Belt objects like Pluto that we haven't discovered, because they would become more loosely packed, so to speak. The distance between each orbit is going to be much greater. But if you went all the way out to the edge of the solar system, there'd be many, many more Pluto-sized planets, most likely. The amount of exploration in space is unbelievable, but we would need much faster spacecraft. And luckily, in this class, we'll be turning our perspective to, greater distances and outside our solar system starting next week. Okay, but first we got to get through these. So I'm going to get back on track and talk about our first moon in focus here around Jupiter, which is Io. I made a big deal about it being dense and being mostly rock. So do remember that. It has a very trace atmosphere of sulfur dioxide. So this is not a significant atmosphere at all. And it's mostly being created continuously from volcanic eruptions because there is significant ongoing volcanic activity. So when we talked about Venus and it being a big deal that one volcanic eruption was potentially, seen in recent times, well, on Io, it wouldn't be a big deal at all. Volcanic eruptions occur all the time, and we expect them. The rock is kept molten. The reason there is so much volcanic activity is that, the rock right in the upper mantle is kept absolutely molten by strong tidal heating. All right. And so if you're wondering why I said, rock in the upper mantle, right? Isn't the mantle solid? Well, it's that whole thing that, you got the liquid outer core, but then there's always going to be some amount of melted material at the very, top, because you have to have magma chambers after all. And so it's, it's basically, I guess, like releasing the heat from within and having, that channels of liquid making its way to the surface. But overall, the heating is happening because of this thing called tidal heating. That's where all the heat comes from. And okay, I have to point out that this is important because if it wasn't for tidal heating, if you took Io and you put it in orbit around the sun, right? So you made it like a dwarf planet, it would be completely cold. It would have no volcanoes because just given the time since the solar system formed, all of that heat would have from the formation, right? The leftover heat from formation would have escaped into space as the planet, tended towards an energy equilibrium. And it would just become a very cold planet and solid all the way through to its core, like our moon, right? And Pluto. Okay. So that's especially true because of its composition, because it's made out of material that has a high melting point. So it takes a lot of heat to actually melt its interior. So when scientists first discovered these volcanoes and they knew about this actually very basic idea about how long it takes a planet to cool. And I say very basic because it's just a universal concept that the surface to volume ratio of objects says that smaller things cool faster. We even know it in our everyday lives, right? When we think about heating up food or baking things, that's being bigger and then thus proportionally having more enclosed volume makes a big difference in cooling time, right? So these small worlds should cool really fast. And so finding one that isn't really demands an explanation. So then, that scientists realized that it had to be this effect, this gravitational tug. So, quick question. Where did the sulfur dioxide in the terrestrial planet's secondary atmosphere come from? So sulfur dioxide. Okay. I won't check the chat, but take another second to think about it. Where would we see sulfur dioxide? It sounds familiar. We've talked about it before with atmospheric evolutions. Outgassing. All right. It was one of the common things that we saw when we talked about those secondary atmospheres for, the planets, the terrestrial planets. And both carbon dioxide and sulfur dioxide are outgassed by molten rock. Okay. So that's where, all the carbon dioxide comes from in the first place, right? That is why it's such a big component of all those secondary atmospheres. But Io's atmosphere only has sulfur dioxide, doesn't have any of the carbon dioxide. Okay. Right? Io, pretty small. Which gas is heavier? Now, you might just know, in which case, well, then you just know. But you don't need to. You don't need to look at the periodic table or know about molecular masses because you can reason it out with the reminder given here and everything we talked about with escape velocity and thermal velocity. And I am going to check on answers on this one real fast. Okay. Okay, so Maxwell says CO2 is the heavier one. Does everyone agree? I'll have to take your silence for yes. Well, unfortunately, it's not. Sulfur dioxide's heavier, which is why it stuck around. Io was not big enough. It did not have enough gravitational strength to hold on to carbon dioxide. And it continues to not be big enough to hold on to carbon dioxide. All the carbon dioxide that is produced through volcanic outgassing on Io escapes into space. Okay. It's that whole atmospheric retention idea. And real fast, Maxwell had a question that we could go into great depth on, but we'll just touch on why did they, so basically early scientists and astronomical societies decide to name the planets, moons, and stars after Greek and Roman mythology. So it's interesting you grouped in stars there, right? Because when we get the star names, yeah, I guess that's a fair point, right? That the individual stars are almost universally named after mythological creatures and characters. Sort of just like there's just a through line, right? They've been named that in Western society for thousands of years, and although there's certainly probably some disagreements and inconsistency, that the idea was to just stick with the most agreed upon name if the star had a name. So that's the idea. There's of course the fact that when astronomy was being, formalized in the 1600s, all right, and then really kind of would have become separate from astrology by that time. You had where was it happening? It was happening at Western universities. So there was obviously a focus on Western history, Western, names. So that's why you didn't see names coming up from other cultures until much later, when there was some sort of more recognition of the fact that, there are other cultures on Earth, right? People seem to have blinders on back then. So I think that's generally the explanation. It's just the where the science of astronomy first took hold. At least, what became modern astronomy. All right. Here is a image taken from space of a volcanic eruption on Io. I love it because it really shows that the size of it, on a relatively small moon with a fairly, energetic volcanic eruption, it's the size of the cloud, it goes into space, right? It's a noticeable proportion of the radius of the planet. It reminds me of a lot of the not to scaled images that when we show, features on Earth that we want to call attention to. And, we show them as being giant compared to Earth. And of course, they're nowhere near that size, but this really is this big compared to Io. Here we're looking at the aftermath of an eruption over a few months in going from 1997 to 1999. So you can see it start here and then spread, right? And then with further ones, there's just a lot of volcanic activities. Volcano on top of volcano, different types. So quick summary about what is tidal heating. I promised that we would explain it a bit more, and this is that explanation that I was referring to. So consider a elliptical orbit like that of Io's. The elliptical nature is exaggerated in this figure just to get the point across. Here we show forces acting on Io with a gravitational force that is greater on one side of the planet because of its, sure, marginally, but significantly closer point, right? So closer means greater force. That's why this green arrow is greater. That causes a stretch of the planet, right? Of course it does, right? Because there's just like we talk about tides on Earth, right? And now what happens as we go to different points in the elliptical orbit? Well, now the directions of those forces change, and that also changes the amount of stretch. So as we go all the way over to perihelion, all right? So it's interesting. So here they call it perihelion, but it's actually aphelion. I don't know how they made that mistake. So kind of frustrating. But also it's not aphelion, because aphelion specifically refers to orbits around the sun. So sometimes that term gets used for other orbits, but more correctly, this would be called apogee for being at the furthest point from the body that is orbiting. And then here, this is perigee at the closest point. So doubly wrong titles here. Maybe just a bad copy and paste job. But back to the images, which are fairly indicative. And obviously the stretching is exaggerated, just as the elliptical nature of the orbit. When we get to this closest approach to the body that's being orbited, in this case, Jupiter, the stretch is more dramatic than it was at furthest distance. So this variation in stretch, this constant flexing, right? Stretching and relaxing, being kind of what we mean by flexing, causes a lot of interior warmth, because that rock is constantly being deformed, sheared, lots of friction forces occurring within the planet. Okay, so that is what we mean by tidal heating. And tidal heating is a big deal for the Galilean moons because of their slightly elliptical orbits, also because of the resonance and thus the pull from the other moons. In the case of Io, that regular pull as it reaches conjunction with Europa and Ganymede just makes it that much hotter, because there's more of this, constant stretch and then relax. So what matters for tidal heating is differential gravity. The fact that the gravity is different on one side of the body to the other. That's why the moon drives tides on Earth, for example, not the sun, right? The sun only contributes marginally to tides on Earth, despite the fact that the actual strength of the gravitational pull on anything on the surface of Earth is about 6 times greater than it is for the strength of the pull from the moon. So the actual strength values might suggest that the sun should drive the tides. It's way stronger, but it's the difference that matters. And the difference from the sun, from one side of the planet to the other, is tiny because they're both really far from the sun, 1 astronomical unit, right? But the moon being only 300,000 kilometers, I mean, that's much closer. And so the difference from one side of the planet to the other is much greater. Therefore, it's what matters. Okay. And this idea can actually be formalized, and at least in an approximation, in the following formula given here, which if you see in the homework, that's where you'd be responsible for it. Otherwise, not too much. Okay. So if it shows up in the homework, be on the lookout for it. But otherwise, don't worry about the equation. But quickly to show, it's the difference in force. So that would be the difference between one side of the body to the other. In the case of Io, right, from one side of the planet to the other. Like, so, equatorial distance straight across, one diameter being the difference. And so the variation in force is equal to 100 times the mass of the body that's being orbited, in this case, the planet, the mass of the moon, Io that we were just talking about, then D, and notice that in parentheses, it's all relative to Earth, right? So another case. D is going to be the diameter of the moon. So Io, for the figures we were just talking about, Earth, moon, if we're talking about Earth and the Earth-Moon system. And then R is the orbit radius. All right. So D is the moon's diameter, and then R is the semi-major axis, which approximately is the radius if the orbit is being approximated as circular. Right. So this just shows the proportionalities about what happens as you change different values. And if we look at the differential gravity for the different Galilean moons, right? So the moons of Jupiter, we see that by far this differential force measured in petanewtons, right? If we're using all base units for the inputs of M, M, D, and R, is 543,000 petanewtons. So, huge differential force, thus a very significant tidal heating. And for the moon, it's tiny, okay? And that's why there's not tidal heating on the moon. And that's just simply put because Earth isn't big enough. The moon is, orbiting the small terrestrial planet instead of a gas giant, okay? And so does the moon, exert significant tidal heating on us? No. But since we have liquid water, we see tidal forces, right? That, causes this actual rising and lowering of the oceans on the surface because it doesn't take much force to do that, okay? But actual heating of the interior, the moon does not do. As far as the differential gravity and its implications to tidal heating, we'll look at Ganymede, Europa, and Callisto. Well, Callisto, being so far out, is going to have very little tidal heating. With Europa and Ganymede, there is. So we should expect some warm interiors for Europa and Ganymede, but not nearly as warm as for Io. Io is a special case, right? This value is huge because of just Io's very close proximity, and then, of course, exacerbated by the resonance. And so it just keeps Io just super hot, right? And which is fine for Io, right? But does mean that you couldn't really live on the surface of Io. It's just too volcanically active, or even have like a base, right? Okay, so we should expect tidal heating. We're going to see tidal heating again as well. There are just lots of these moons are kept way warmer than we would otherwise expect. So tidal heating is this powerful and meaningful phenomenon because it essentially keeps these moons from becoming totally dead. And the natural comparison is Mars, right? If Mars had tidal heating, it absolutely could, probably sustain liquid water because it would have, all these processes of, pushing heat up. It might have plate tectonics for that matter, right? And so it's almost like this tragedy of the solar system that this great, large body, it doesn't have any tidal heating because it orbits the sun and at a very great distance. So, comparatively, so that it just had in the 4 billion years, 4.5 billion years since it was formed, it's just totally cooled. So the interior of Mars is thought to be solid all the way to the core. There's no molten left. And if that was the case for the moons of the Jovian planets, they wouldn't be that interested, and scientists wouldn't be that interested in them. But once it was discovered that tidal heating is so prevalent, it really changed the game in terms of what we might expect, what are the scientific goals and interests of these moons. Now scientists regularly talk about the potential of life on these moons. Why? Because there are, as we'll just see in a moment, subsurface oceans. How are there subsurface oceans of liquid water, by the way? Because of, you guessed it, tidal heating. And I could say because of differential gravity, but it's often like I say tidal heating as a stand-in because the very next logical step is differential gravity causes tidal heating. So then we talk about the consequences of tidal heating, but we could talk about the consequences of differential gravity. Just, it doesn't sound as catchy. And then if that wasn't enough, the search for, honestly, very simple life, right? So the expectation isn't to find like some advanced life form living in these subsurface oceans, but rather to find maybe, just any existence, bacteria for that matter. There's also, because of liquid cores, magnetic fields. So we have moons that are generating their own magnetic fields. And in some cases, like in the case of Ganymede, generating a magnetic field and then also existing within the magnetic field of Jupiter, which means that the surface of Ganymede is incredibly well protected from the solar wind. And the solar wind itself isn't that harmful, but when it interacts with an atmosphere, can then cause these cascading effects to generate really harmful X-rays and UVs, so UV light. And if that's not the case, if the solar wind can't make it to Ganymede, because Ganymede is doubly protected by both the magnetosphere of Jupiter and its own magnetic field, well, it doesn't have an atmosphere, but if it was given an atmosphere due to human terraforming, it would be able to hold on to it much better than Mars. The only viable way to ever terraform Mars would be to create a magnetic field, which would have to be done with some sort of satellites and is totally science fiction and probably not even possible. But Ganymede is already ready to go. So interesting things to think about. So tidal heating of Io, which of the following is not a factor explaining why Io experiences such substantial tidal heating? Take a quick second to answer yourself, but I won't check the chat. Right, so hopefully one stood out. It's the inclination, right? Not relevant to the to tidal heating, and being inclined wouldn't help, All right, now talked about Io. Next up, Callisto. So we jumped from the closest to the furthest. Callisto is all rock and ice, just like those moons of Uranus. Density is pretty similar, just a little bit denser than Tatiana and Oberon. No atmosphere. Okay. Nothing, even though it's fairly big, whatever outgassing occurred, although might not have been much outgassing with the composition that it has. But there is potentially some amount of ocean under its surface, but it would be pretty minimal. So is water ice more or less dense than liquid water? Well, think about, do ice cubes float? Do icebergs float? Yes. Therefore, ice must be less dense, which is unusual. The solid state of materials is almost always less, more dense. Like solid gold is denser than liquid gold, and many other examples. But water has a strange property due to its basically polarizing bonds, and then it actually becomes less dense as a solid. And its densest at 4 degrees, above melting. But anyway, so that has this whole property of water, which is scientists have long talked about and think is super fascinating and kind of makes water stand out as being important for sort of facilitating these processes of energy exchange and nutrient exchange, which seem to be important to life. Okay, And so that's why when we see liquid water, it's a big deal on another planet, and we can find it underneath big ice sheets. So when with the moon, we're just about to talk about, we're going to talk about water underneath a layer of ice, and that's made possible because of this property. And Callisto is slightly larger than Earth's moon, but has much more ice than the moon, and so which has a higher density? Well, there you go. It's got to be the moon, having much more rock than ice. Okay, so now moving on to Ganymede, the biggest moon in the solar system. All right, it doesn't have an atmosphere. And this is really like not necessary. There's no reason to think that it couldn't have an atmosphere. It seems to just be a fluke of its formation that whatever atmosphere was formed because of early outgassing, it did not retain. Under probably slightly different circumstances, it could have kept its atmosphere, but it did not, and it is therefore vacuum of space on the surface. Okay, but it does have its own magnetosphere, not terribly strong, but as I said, it's also within Jupiter's. Okay, it has a warm molten interior, which is how its magnetic field is formed. So it's formed from that dynamo effect of the melted rock within. It also has a large subsurface ocean. So underneath the layer of dust, rock, and ice mixture, and under a rather thick layer of that, there is a subsurface ocean. When we look at the surface, we see evidence of stretching and deformation. So definitely some erasure of impact craters, but not as much as Europa, which we'll talk about last. All right, and what causes the Earth and the Jovian planets to create their own magnetic fields? Well, I said it's the movement of materials inside the planets. Okay, that's not the only, necessary component, but of the list here, right? It's not having lots of iron. It's not heat from its magma. It's not the free electrons and metallic hydrogen, because that's how Jupiter and Saturn generate their magnetic fields, but not the terrestrial planets nor Ganymede. And all right, and so then it is the movement of the materials. And I guess it does say the Jovian planets. So not sure why it lumped those together. I would say it is the free electrons in the metallic hydrogen for Jupiter and Saturn, but it's the movement of the ionic ices for Neptune and Uranus. So a little bit of clarification necessary there. But the movement is absolutely necessary because you have to essentially be building up that static electricity. You have to generate that charge, and then the rotation creates the circular current. Okay, and this going back to differential forces to explain, that the fact that there is a significant amount of heat inside Ganymede. Here are the layers of Ganymede. So that there's that subsurface ocean. It's almost like just a whole layer of melted water. Iron core, liquid outer core. So finally on to Europa, right? Last of the moons of Jupiter that we're going to talk about. No atmosphere, which has been true of all four of the moons. It has a liquid ocean under the surface, just like Ganymede, but much closer to the surface. So the ice that we're seeing is really like ice sheets, like you would see at the North Pole of Earth, at least somewhat similar. And they're essentially floating on a ocean of liquid water. So instead of it really being like deep down underneath a thick layer of crust, it's more like fairly thin ice sheets floating on an ocean that covers the entire planet. Well, not planet, moon. There's all types of surface features because of the ice. As the ice rubs against other sheets, breaks apart, subducts, and so on. There are some craters, but they don't last that long because the surface is constantly being recreated, right, and refreshed. When we look at its interior, it does have a metallic interior, and there's that much thinner but closer to the surface ocean that makes Europa popular for study, because it just seems like really, potentially a ocean that would have the right amount of heat, the right kind of like conditions for nutrient distribution to support life. And the life could evolve there completely independent of life from the sun potentially, because that's what is thought to have happened with the subsurface vents at the bottom of Earth's oceans. We haven't talked about them. If you've heard of them, they're these vents that have specialized life form, often called extremophiles, that live around them. Called extremophiles because it's a boiling hot water environment. But because of the nutrient-rich nature of it, there are whole ecosystems that rely on these essentially little volcanic vents where boiling water is coming up out of the bottom of the ocean floor. They tend to happen near those Atlantic ridges, which we did talk about, or rather oceanic ridges, like the Mid-Atlantic Ridge, where the oceanic plate is splitting apart and being renewed, being recreated. And those life forms, they don't need sunlight, and their entire food chain doesn't rely on anything to do with terrestrial life. And so it's maybe where life started on Earth, or at least sort of has developed and continues, not always independently, but could be totally independent. So as I said, very low cratering because the surface is always getting refaced. All right. Very clean lines, some split ice that's refreezing. That makes that particular interesting surface features. The warm spots under the surface, show that the water, has convection. It's like, there's obvious movement of water currents happening in the ocean. And the Europa, just like Ganymede, has its own weak magnetosphere. There was a mission launched by ESA and a more recent mission launched by NASA just this year called the Europa Clipper. So lots of active research trying to study, not land yet, but do close flybys and temporary orbits to really, figure out as much as they can with radar imaging and trying to catch samples into space about what may be going on with these subsurface oceans. And could they really support life? Finally, on to another moon. There's a lot to talk about with Jupiter. Neptune. So the only moon that we were interested in that orbits Neptune is Triton. Sorry, all the other moons. But Triton is a pretty special moon because it's quite large, unlike Neptune's other moons. It's rock and a lot of ice, kind of has a similar composition to Pluto. Its density is a little bit greater than Callisto's for comparison, but it's sort of similar in composition. What makes it stand out is that it has a retrograde orbit. It does not orbit in the equatorial plane. So that tells us, unlike the concept question we had before, that this is not a moon that formed by accretion. This fact, the retrograde orbit, the fact that it orbits the other way, totally excludes the possibility that it could have been formed by accretion. It had to have been formed by capture. So Triton must be a gravitationally captured body. The best guess is that it was a Kuiper Belt object, since it does have so many similarities to other dwarf planets in the Kuiper Belt. It has a thin nitrogen atmosphere that is sort of continually renewed by nitrogen geysers. There is no tidal heating. It's kind of the exception almost, because tidal heating is a big deal with a lot of the moons we talk about, but not in the case of Triton, mostly because it orbits fairly far away. And that also holds for accretion. When you look at large moons that were formed by accretion, they are by definition close, because that's where the accretion disk was dense enough, in terms of enough particles per square meter, right? There's enough matter to make significant bodies, large moons. There's just that as you go further out and the radius of each orbit gets bigger and bigger, there's just less rocks, per meter, less dust per meter, whatever. But closer in, there's plenty. Triton didn't form that way, so it can be really far out. It doesn't have to be due to capture, but usually is, because otherwise, if there's some sort of gravitational capture that leads to a moon swooping into what would be a close orbit, probably just lead to a collision. And all those things took place in the early solar system when all the stray pieces, were getting, crashed into each other and then reaccreted, right? If, two bodies split apart completely. So Triton didn't, since it came in later and stably, and it's too far out from Neptune to experience tidal heating. Not to mention Neptune's not that large, right, compared to Jupiter. So it'd have to be much closer if it did want tidal heating in the first place. Despite that, there is enough heat for the geysers. They seem to be stimulated by sunlight because they occur on the sunlit side of Triton. And on the side that's in darkness at any given point, there is not any amount of these nitrogen geysers. Doesn't take as much energy to turn solid nitrogen into liquid nitrogen. That's why this phenomenon can happen at such low temperature and without any internal heat from the planet. Here are the evidence that almost look like burn marks of the nitrogen geysers. So they leave this this sort of black dust. And I'm not sure what molecular process causes it to become so dark, but I'm sure that's sort of it's not directly the nitrogen, but rather a molecule that forms. Now, when we talked about the circular orbits not being supportive of accretion, I said that we'd see a circular orbit of a body that was not accreted but captured. Well, that's Triton, because Triton has this ridiculous orbit. It has an eccentricity of 0.000016, which means that it's very, 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 kind of gave it away, but this one, circular. It just has a really, really low eccentricity. Few things are that close to a perfect circle. So without an eccentricity, then any chance that it would have tidal forces is then completely doomed, right? So even if it was closer and Neptune was bigger, you need some eccentricity to sustain tidal forces, at least the kind that really keep an interior of a planet molten. Sublimation, though, is what drives those nitrogen geysers. Sublimation is quickly discussed here because it involves turning a solid directly into a gas. So that's the sunlight, hitting the surface and causing a phase change that skips over liquid. So points out that carbon dioxide does that on Earth, in Earth's atmosphere. Water would require a much more of a vacuum. It would require a pressure that's 1/165th of Earth's atmosphere to sublimate, just to turn to just boil at room temperature. But you can do that. You can create a vacuum with a pump in a good chamber and cause water to spontaneously boil. And then nitrogen needs a low pressure, but not nearly as low, just 1/8 of Earth's atmosphere. And then it can spontaneously boil. It can just turn from a solid into a gas. Triton totally meets that criteria. It has an incredibly thin atmosphere, almost non-existent. So it's easy for the nitrogen to undergo this process of sublimation, thus driving those geysers. What about Saturn? Okay, Saturn has a bunch of interesting moons, but we just want to talk about Titan. I'm just going to quickly summarize here as last 2 minutes. Titan is famous for its atmosphere. Super big deal. It is the only other, world except for Venus, right, that has a significant atmosphere. Literally, there are 3, like non-gas giants that have significant atmospheres: Earth, Venus, and Titan, right? So that's a small grouping, and you might not know, right, that the third is some moon of Saturn. It is a large moon, as we saw, right? Second largest moon in the solar system, and it has a thick atmosphere, but not thick and like just creating devastating amount of heat like Venus, but thick, causing some amount of insulation, but still very cold because of where it's located in the solar system. But it creates a whole cycle of basically liquid flow, precipitation. There are lakes, rivers, seas, and rain of methane and ethane. So methane and ethane play the same role in terms of erosion, precipitation, cloud cover that water does on Earth. There are underground oceans also of methane and ethane. All right. And tidal heating, right, is definitely the explanation of, sort of creating these conditions, because Titan has a weak magnetic field, which is how it can have an atmosphere in the first place. Invisible light, you can't see through the atmosphere. Images like this are taken with infrared, which is the only way we can see the surface features and see those kind of like lakes of liquid methane and ethane. Lots of valleys, future missions are actually going to this planet. There's NASA plans to send a helicopter, a robotic helicopter to fly around because the surface is too rough for rovers. There are seas, small seas, large lakes, whatever you want to call them, of liquid ethane and methane. All right. Last thing I'll point out, because this is a kind of a fascinating idea, that tidal locking is incredibly common. Every moon that we've talked about, with the exception of potentially Tatiana, is tidally locked to the body it orbits. So that is an incredible generalization to make, that every large moon in the solar system is tidally locked in that it always has one face that faces the planet and one face that faces away. So this seems to be just a very common orbital state to reach when there is a relatively large moon. It almost seems inevitable. Okay, so we're out of time. We'll end there. And thank you for the circular answer, Maxwell. And we've covered as much as we're going to for chapter 12. Good covering. And just real fast, I'm going to stop the recording, but just to give you a heads up,